Now let's look at example 2. Here we have a mass sitting on a table, frictionless table. It's connected via a rope over a pulley to a second mass. Now gravity is pulling down on mass 2, so it's going to fall. Via the tension in the rope, it will pull mass 1. So this is, again, a system of connected objects. This time, the objects are connected with a rope. And the thing to know about ropes is that the tension force is the same everywhere on the rope. And the acceleration is the same everywhere on the rope. If that weren't the case, then different parts of the rope would be moving at different rates, and the rope would be stretching or breaking or something. So whenever you have a rope or a string, you can always assume that the tension is the same everywhere, the acceleration is the same everywhere. In fact, the velocity and displacement are also the same everywhere on the rope. So we analyze this problem using our same method. We draw separate free body diagrams for each object and then do our Newton's second law analysis. So let's start with mass 1. Horizontal, vertical coordinate system. Place mass 1 in the center. There's several forces happening here. Gravity, of course, is pulling down. There's a gravity force, the Earth on mass 1. There is a normal force of the, I guess we'll call it a table on mass 1. The y direction doesn't really matter for mass 1 because there's no friction involved and there's no acceleration in y. What does matter is the tension force in the x direction. That is the tension force of the rope pulling on mass 1. So the Newton's second law equation in x for mass 1 says that the sum of the forces on mass 1 equals m1 times a1x. I'm being careful to give these the proper labels. And there's only one force in the x direction. It is the tension force of the rope on mass 1. And as usual in these types of problems, we are currently stuck because there are two unknowns in this equation. We don't know the value of the tension force, we don't know the value of the acceleration. So let's leave that be for the time being. We'll look at mass 2 now. Here's its free body diagram. Mass 2 is at the center. There's only stuff happening in the y direction, nothing in the x direction. In the y direction, we've got gravity force of the Earth pulling on mass 2, and you've got the tension force of the rope pulling on mass 2. So Newton's second law says the sum of those forces in the y direction equals m2a2y. We've got tension in the positive y direction, pointing up, and gravity in the negative y direction, pointing down. And once again, we're stuck because we don't know the value of t, we don't know the value of acceleration. Let me substitute our usual formula for gravity in there. It's m2g. We're still stuck though. now we have to use some of our common sense about things. The first bit of common sense is to remember what I told you about ropes and strings at the beginning, which is that the tension force is the same everywhere on the rope. So that means that TR1 has the same value as TR2. So let's just ditch all the subscripts and call it T, because it's the same thing for both. And now the slightly trickier thing to note is that both objects have the same magnitude of acceleration, but we need to pay attention to how we drew the coordinate systems. So the magnitude of A1x equals the magnitude of A2y. We'll just call that A. But if mass 2 is going down, in the coordinate system we set up for mass 2, down is the negative y direction. Mass 1 is moving to the right. In the coordinate system we set up for mass 1, that's the positive direction. So, without these absolute value signs, A1x would be positive A, and A2y would be negative A, because we defined the coordinate system for mass 1 as being positive going to the right, and we defined the coordinate system for mass 2 as being negative going down. So with all these values defined, we can substitute into those two equations where we had gotten stuck before. So this first one becomes T equals M1 times positive A, and this other one becomes T minus M2G equals negative M2A. And now we have a system of equations you can use your favorite algebra technique to solve it. I'll use substitution. I'm going to substitute this value of T into the second equation. Now I'll do a little algebra magic. And I can finally solve for the acceleration. After all that work, the final answer we get is not that complicated. And in fact, if you were to think about this a little bit, you might be able to guess that answer. This answer is saying that the acceleration of this system of objects equals the gravity force on mass 2 divided by the total mass of the system. Going back to this picture, if we just think of a broad perspective about what's going on, the reason why the system moves is because gravity is pulling down on mass 2. That's the only reason why this thing would move. Gravity is pulling this object down. That causes mass 2 to fall. Because it's connected with a rope, it pulls on mass 1 to the right. So the force that makes everything go is the gravity force on M2. And it's a system of two objects. The total mass of that system is M1 plus M2. So makes sense that the acceleration of that system would be the force on the system divided by the mass of the system.